on the third day of ADMET 2022. So here we have our eighth technical session of this event. This session will be chaired by Dr. Vikram Kumar and co-chaired by Dr. Sushil Kumar. Dr. Vikram Kumar sir has been the ex-director of CSIR NPL, ex-director of Solid State Physics Laboratory DRDO, and has been an emeritus professor at IIT Delhi. Dr. Vikram Kumar is well known in the area of semiconductor materials, characterizations, and device technology. His extensive work towards the understanding of electronic defects and interface states in silicon and semiconductors lead to the prestigious Shanti Swarup Bhatnagar Award in 1992. He led the setting up Gallium Arsenide Enabling Technology Center, Foundry at Hyderabad, for the pilot production of monolithic microwave integrated circuits. Under his leadership, CSIR NPL achieved international equivalence in metrology. He has been responsible for setting up nanoscale research facility at IIT Delhi. He has published over 190 papers in peer-reviewed journals. Dr. Vikram Kumar is a fellow of NASI, INAE, and IETE, in addition to being a member of several professional societies, some of which he is presiding. He was recognized as the Distinguished Material Scientist of the year 2012 by the Material Research Society of India. He has received an honorary DSc from the Indian Institute of Engineering, Science and Technology, Howrah. So I request you, sir, to please clear the session.
Thank you for the introduction, and let's start the first session today. And it's my pleasure to introduce Blair Hall. Mr. Blair is working as a metrologist at the Measurement Standards Laboratory of New Zealand. He leads the MSL's digital metrology program. He's trained as a physicist. He holds a doctorate from École Polytechnique Lausanne, Switzerland, for research on atomic structure on nanometer-sized particles, and later worked as postdoctoral fellow at Swiss National Metrology Institute, MITAS. He returned to New Zealand in 1993 to lecture in physics and electronics at Massey University. Then in 1998, he joined MSL. So we invite Professor Blair Hall.
Thank you very much, Mr. Chairman. Hopefully you can now see my screen. I'm getting quite a lot of echo on the line. Perhaps you could turn off your microphone. So I'd like to thank the organizers of the conference, in particular Dr. Jaiswal, for inviting me to participate in this meeting. Sorry, technical problems. There we go. So I think you'll all be aware that we are at the very beginning of a global process to transform our international scientific and quality infrastructures so that they operate seamlessly using digital technologies. And here on the right of my slide, you can see a number of logos representing various international organizations involved in the international quality infrastructures who have recently joined a joint statement of intent to try and collaborate to establish a worldwide exchange format based on the ESI system of units. So in my talk today, I want to look at that activity, and I want to focus some attention on the more scientific aspects of it. In particular, I'm going to talk about first where I think the value of traceable measurement is actually realized, who traceable measurement is really of value to. And then I'll say something about the challenges that we face in terms of digitalization, but at the metrological level. And then finally, I'll just speculate a little bit on some of the opportunities that I see for digital transformation in metrology. So if you were to ask an economist where the value of traceability arises, this is the sort of response you might get. This was copied from a document published by the World Bank and draws attention to facilitating market access, enhancing productivity, achieving public policy objectives, and that sort of thing. This is all very well, and it's all based on the underlying trust in the accuracy of metrologically traceable measurements, the special feature of those measurements. Well, if we are to succeed with our project of digitalization, I think we need to go more deeply into an understanding of what traceability is. And I think we must understand exactly what is valuable about traceable measurement and to whom it is valuable. So for critical decisions in our society, traceable measurement is mandated. And that's because our understanding of physical systems is a scientific one, and we use measured data to inform decisions based on our understanding of actual real life situations. So to illustrate the idea, rather humorously perhaps, here on the right-hand side of my slide, we can see a loading truck which has toppled over. We can be sure that the stability of this machine can be evaluated based on physics principles, and so one would know how much load such a machine can carry without becoming unstable. And what I really want to emphasize to you is that what happens in the real world happens, and it's not nominal values. It's not the nominal value of the measured weight of the container or the perhaps the incorrect evaluation of the stability of the little truck. The real world has its own laws. So what's important in traceable measurement? We all know that a measurement procedure provides us with a measured value, but that is not the same as the value that we intended to measure. It's not exactly the same thing. It's an approximation. And so there is always some measurement error. And the particular feature of traceable measurements is that we characterize the likely magnitude of that error. And we provide an objective statement of uncertainty that reflects the accuracy of the measurement. So that allows people to make decision procedures, to design decision-making procedures that are reliable. And here's an example that I think we can all easily relate to. It's the idea of speed regulation enforcement. If a vehicle is actually traveling less than the legal speed limit and we measure the speed of the vehicle and obtain a result that does not lead us to issue an infringement notice, then that's a good decision. Similarly, if the vehicle is traveling faster than the limit and we measure it and we decide to issue an infringement notice, that too is a good decision. But if the vehicle is traveling within the legal limit and on the basis of our measurement, we decide to issue an infringement notice, then that is a poor decision. And similarly, if the vehicle is speeding and we don't issue an infringement notice, that's a poor decision. So it's only because we have information about the likely error in speed measurements that we can design a process that can be considered fair and objective in order to achieve the societal goal of safety. So that's the sort of thing. At the end of the measurement chain, we do things with the data that are of benefit and are of value. Well, getting back to the quality infrastructure, we can think of that as a collection of institutions that work together to establish standardization and conformity assessment and that sort of thing in society. At the basis of all this is metrology. There's a scientific basis for the success of this infrastructure. And if we are to transform it and digitalize it, we need machine readable, executable documents with interoperable representations of metrological concepts. These are not concepts that come from information technology. They're our own metrology. And so we need metadata for communication among these institutions and scientific communities. Well, at present, our systems are essentially paper-based. They are oriented towards expert people who work within the infrastructure. They tend to be technically specific to particular areas and adopt formats that people working in those areas expect to see. What we need to develop are much more standard representations, digital records that are based on our scientific knowledge of metrological concepts. Now, this is a quote that I like to use because it reminds us that if you don't have a clear understanding of what you're trying to achieve, such that you could explain it to another person who is perhaps not an expert in the domain, then what hope do you really have of explaining it to a computer? Computers need strictly logical instructions. So we need logical, correct representations of things like traceability, units of measured quantities, their value and uncertainty. And once again, I want to emphasize, these are the metrological concepts that we metrologists have responsibility for. Well, getting back to traceability, on the right here we have the familiar representation of a traceability pyramid with at its summit the definitions of our measurement units, and then the realizations, and then the dissemination through our calibration laboratories, through to the end users in industry and testing laboratories and so on. Well, if you think about what I said to you a couple of slides ago, it's at the base of the pyramid, and only at the base of the pyramid, where we actually generate value from our traceability chains. And so what I think we need to do is to recognize that traceable measurement actually occurs in stages. It's a collaborative process. And the metrology institutes and calibration laboratories only provide intermediate results in a staged measurement process. The full measurement extends all the way to where the decision is made. Now, the way in which we report at the moment has been influenced strongly by the GUM, the Guide to Expression of Uncertainty in Measurement. But it might surprise you to know that we don't actually fully comply with GUM recommendations. Those recommendations were for a universal format that was both internally consistent and transferable. But when we start to look at the measurement as a whole, as a staged collaboration between the various actors, we're not doing what the GUM said we should do. And I think that although I can't find any decision written about that, I think that's a pragmatic compromise. I think that our implementation simply had to take into account that people could only handle a certain amount of data. But with digital systems, it's different. Digital systems can implement the GUM's recommendations. And so this schematic here is trying to convey the basic idea. If each horizontal line here is one stage of the traceable measurement, then influence quantities that arise need to propagate through until the final stage of the measurement. We need to have an uncertainty budget at the terminal point of the measurement chain. And in a digital system, we can use unique digital identifiers to identify both the influences and separately the individual stages. And this is going to allow us to provide what is called FAIR data, data that corresponds to the FAIR principles, which is findable, accessible, interoperable, and reusable. So with digital technology, there is a possibility of really changing the way in which we report our measurements. Now, another problem that we have is the representation of units. And of course, our SI system dates back to the introduction of unit systems by Clerk Maxwell in the 19th century. And he too was interested in interoperability. He wrote that we may be able at once to transform our results from one system to another. So he was dealing with the problem of different unit systems in different countries and the ability to communicate among scientists as efficiently as possible. But of course, in Maxwell's day, he was communicating with skilled scientists. And we today would like to design systems that computers can operate autonomously. So there are some problems. And let me just give you a flavor of the sort of difficulties that we have. So units don't identify quantity. If we had 0.555 hertz, we could also recognize that as 0.555 per second. These are equivalent notations in the SI. But if we had 0.55 becquerel, the unit of activity, that is also legitimately represented in this format, yet the two named unit formats are not compatible. So there are issues like this where the relationship between units is far from clear. Another example, if we were told that, if we were given a value 12 degrees Celsius, do we recognize that as being 12 Kelvin or 285.13 Kelvin? In one case, it would be a measurement of absolute temperature. In the other case, a temperature difference. And we simply cannot tell from the units themselves. So what we need is a digital format for units that can manage legitimate conversions, but can prevent us from making incorrect associations. We need to enhance the interoperability that we have today, which relies on expert intervention. We need to make that something that computers can operate autonomously. And we should try, and I believe we can, extend our units format so that we can incorporate kinds of measurement data that are not catered for in the SI. So this is a problem that isn't really resolved as yet. there are digital format systems in use, but they do tend to be based on the ideas of Maxwell. And this, you can spot this because of their use of dimensions and dimensional analysis in their implementation. And so they all suffer from, from this limitation in their design. So those are two of the really big challenges that only, I think, the metrologists can fix in this digital transformation. And now just briefly, let's look at some opportunities perhaps that are presented. If you accept my view of a staged measurement process, and if we imagine that we solve these problems so that we can connect the stages of a traceable measurement chain with some sort of digital communication channel, then what we have effectively done is created a measurement network. And the nodes of this network, the stages of the measurement, consist of definite quantities measured with definite accuracy. So this should present all sorts of interesting possibilities. It should present systems that can be built with resilience, redundancy, where the system will always be able to assess its accuracy and adapt to changes in its operating conditions. Such a system would be able to immediately benefit from changes to its constituent parts if we put in subsystems of greater accuracy. These systems will be aware of the provenance of influence quantities, and this is a very interesting opportunity because we know that in complicated measurement systems, there are different ways of configuring the measurement which will have different accuracies. And so systems can be self-optimizing to obtain better accuracies under particular conditions. And this is a little bit of science fiction, but I imagine that we could have some sort of interactive measurement where a digital system discovers in its environment the measurement services available and can take action in relation to those services. So here we might be talking about smart health services or smart buildings or something like that. And last but not least by any means for our industrial partners, the cost of ownership of critical measurement systems in today's world is quite high because as these systems age, it becomes more and more difficult to replace components in them, to source and replace components in them. Whereas a system which is effectively designed to manage its own accuracy will be much easier to maintain because equivalent but different subsystems could be substituted in. So to sum up, I think that our digitalization efforts should be looking beyond what we do today. It's not good enough just to copy into digital form what our practices are. I think traceable measurement can be seen as a staged collaborative process, and I think digital records can be used to connect those stages, and I think this is achievable. And in that case, traceable measurement becomes something a little different from what it is today, and that offers us opportunities. So we must remember that the scientific basis for our quality infrastructure is metrology, and so this is an opportunity for metrology to deliver value to the people at the end of the traceability chains who really consume our traceable measurements. So thank you very much. I hope that came through okay. And if you have questions, I'll try and answer them.
Clear talk, very simple, but very important ideas. We are now have time for a couple of questions or comments. Any? Yes, Ashish.
Dr. Hall, we are now gearing towards the digital transformation. All the NMIs are trying to incorporate these ideas. So I like to know that what kind of networks, what kind of data centers, what kind of logistics, what kind of infrastructure and manpower do we anticipate to undertake this digital transformation work? So what is the status of other NMIs in the world? How the infrastructure, the logistics, the data center and things like that, the manpower need to be, need to be changed to implement this digital transformation thing.
Thank you for that question. I may not be the best person to answer that, but I can give you my certainly give you my impression, and that is that there is a huge difference in readiness between different NMIs. And so we see in Europe, for example, that the German NMI has really focused all of their resources, let's say. I think that they would say that everybody who works in the PTB laboratory has some interest in digital transformation. So that's a truly massive effort. And so they are trailblazing, but many other NMIs are not. And I think that part of the reason for this is that the very fundamental questions that I've touched on in my talk really need to be answered before a great deal of actual investment takes place. So we metrologists are not going to be expert in all of the technology that needs to be developed, but we do need to be able to clearly guide the work, define the work, specify the work so that it is done to our satisfaction. And so that the decision to do that will be made by the different NMIs. And so I think you can see that some NMIs are sitting and waiting to have a clearer picture of what actually has to be done, so that almost they're waiting to be told what you need to do. And other NMIs like PTB are really trying to develop technologies that will be incorporated into a much wider scheme of things. So there are two groups at the moment, and of course over that there is activity at the CIPM level, and I'm involved a little bit in that, where there is a task group who have been looking at questions like the units of measurement and things like that. But that work is ongoing, so it hasn't actually delivered a clear answer that NMIs could act on. So it's a difficult situation. You can easily get involved as an NMI at the moment, but it's not entirely clear what you should do.
Okay, any other? Yes.
I have a question regarding this digital records. So one of the important components of digital transformation is going to be the digital calibration certificate, right? And that has to be universally acceptable and interoperable. So in this regard, many NMIs have already started working in this direction. But as I believe, and I heard from your talk, that there has to be a universal format for this. So does it make sense to, start working on this, or one has to, just accept one universal format for this?
Well, thank you for that question. I hope you will have a talk, I think, later this morning from Sasha Eichstadt, who will explain to you the PTB point of view, and mine is a little different. So please bear that in mind. In my view, it would be a backward step if we all have to use exactly the same digital calibration certificate. If we are confined to a particular format. And so what I have tried to hint at in my talk today is that there are actually underlying concepts which are much more basic. So if you can digitally represent a quantity and the units and its uncertainty, and these are elements that you have digital metrological tools that manipulate these, then I think that we will have more fluid ways of communicating data for different purposes. So you can already see that in the European activities, they have been working hard on the DCC, but they're now looking at requests for calibration and other kinds of digital document. And so I think that what's going to happen is that if you think about, we all take this for granted, but if you think about your computer and the fact that it can do simple mathematics with real numbers, that is a digital representation, and it's implemented on a device that uses binary representations and registers and all the rest of it. It's a representation of a mathematical concept, and I think that there are some concepts at a similar level, like uncertainty in a value, which need to be very, very primitive so that we can incorporate them in different kinds of document and communication. So that's my vision. It's a grand vision. It's not for the end of the year, but I think that's where we should be thinking of going.
Right. Thank you.
Yeah, sir, your talk is really excellent and is paving way for the network architects to construct the networks, which will be definitely gonna weave the whole nation across the globe into digital transformation. But my questions are to this is the last word you had concluded that finally we are going for a digital transformation with a dynamic network. So dynamic word in the sense is a robust or is a kind of ever increasing network which is constantly increasing the nodes across the whole globe, sir.
I'm not sure that I quite understand the intent of your question, but when I described a dynamic network, I'm not a network person. I have a simplistic picture in mind. And so if you think, one of the ways that I try and explain this idea to people is if you think of an aircraft flying, approaching an airport, they have to maintain their altitude within certain tolerance levels, otherwise they'll crash into other aircraft. And so they have instrumentation that does this, but the accuracy of that instrumentation isn't managed in a smart way, if you like. So I say to people, well, imagine if you have one of these altitude measuring instruments and you can plug it in to your system, and your system is immediately aware of the accuracy of that instrument, then the aircraft can be used in a different way than before with a different accuracy instrument. So I'm thinking of systems that, because they are aware of the accuracy of their components, can adapt dynamically to whatever is happening. It's in that sense that I used the word.
Yeah, I got it, sir. Thank you.
So thank you very much, Dr. Hall, for excellent discussion and the talk. Very important. So thank you once again.
My pleasure.
So now we have time for the next speaker. Next speaker is Professor Venugopal Chanta. Venugopal is now currently the director of Indian NMI, the National Physical Laboratory. He did his MSc from Central University Hyderabad, then obtained PhD in physics from TIFR in 2000, the year 2000, and then in 2006 he was awarded PhD in electronics engineering from Tokyo University on design and demonstration of an ultra-fast all-optical switch. So he's been in TIFR faculty from 2004, where he was a professor before joining NPL, India. So Professor Venugopal.
Thank you. Thank you, Dr. Vikram Kumar and MSI for giving me this opportunity. I've been asked to give more of a status of activities at NPL. So I'm just a little older than a year at NPL. So this is more like my own progress report. Right. So I would like to acknowledge contribution of all staff members of CSR NPL. So we have organized the NPL, which is NMI, in 6 different divisions. So we have the physico-mechanical, electrical, environment, material, device, and Bharati Nirdeshak Dravya, which are the reference materials or the certified reference materials, and the Indian Standard Time, which is there. So these are all supported by the Center for Calibration and Testing and the business development groups. So the current status of the SI units are, these are the 7 units as we know, and these are the standards which we have, and these are the uncertainties which we have in each of these units. So MOL we don't have right now. Right. So as we know, from 2019, we moved to the quantum metrology definition. So we're looking at when setting up these things at CSR NPL. So just to give a current status of new SI realizations across the globe. So these are the SI units and the name of NMIs. So the ones in purple, so they are the ongoing activities in the Asia Pacific region. So we are working on this Kelvin and the gas thermometry, the balance, and the quantum current measurements and the meter for the interferometry based ones. Right. So just to give a brief report, like so the 10-gram 10-gram prototype of cable balance has been worked upon. It's not really a mass standard, but at least it gives estimation of Planck constant to reasonably high accuracy. So now we are looking at in-house development of 100-gram cable balance. So hopefully we'll move on to the 1 kg in the next few years. So the acoustic gas thermometry, the asymmetric cavity is designed and fabricated in-house. So now we are, I mean, the Q factor everything is estimated. Now we're moving towards the measurements. So hopefully in the next 1 year, this will be completed. Right. So in other physicochemical parameters, so what we have set up in the last 1 year in the robotic mass comparator, these have been installed, a 200 kilonewton force standard. There's a C-type goniophotometer, which is also linked to this optical radiation test system. So this can measure up to 2-meter light sources. You can calibrate, calibrate them and test them. This is a base for the pneumatic DWT. So this is the density measurement setup, which is also operational now. So these are other things which have been done. For example, we have developed this blood pressure and clinical thermometer test calibration and pattern approval testing system. This is developed for the RRS Silvarnas, which it has already been installed. And it was inaugurated by the Prime Minister in December 2021. So this is, they asked for a manually operated one, but our team has successfully delivered a semi-automatic, which can be also operated in manual mode. So now the next generation is also ready now in fully automatic operation mode. Right. So this is also they've developed this new ultrasonic energy meter calibration facility. So we have a variable ultrasonic and energy level setup where we can go up to 100 watt per centimeter square. The idea is to ramp it up to 250 watt per centimeter in the near future. In the electronics and electrical metrology division, so the major activities which have been accomplished in the last 1 year include the participation and completion of intercomparison of standard resistors 1 ohm and 10 kilo ohm. And the Xenon reference voltage standards 1 volt and 10 volt measurements have been completed, and currently the report is being prepared. So in addition, the three-phase power comparator and high current amplifier have been installed, and we are working with the local Delhi research, implementation and innovation, which is a Section 8 company. This is the drive, which is identifying the local problems, and we would like to contribute to that. We are in constant touch with them related to the Ministry of Power identified areas, mainly the modern technologies like smart meters, prepaid meters to improve customer experience, calibration of these, and the adoption of superconducting and magnetic materials for different applications, and also work towards the charging infrastructure and technology options for vehicle to smart grid connections, right? So in the air monitoring, we have the gadget release where CSR, National Physical Laboratory, is designated as the National Verification Agency for certifying instruments and equipment. This is for monitoring both emissions as well as ambient air. So there is a calibration facility for ambient ozone analyzers, which was inaugurated or launched for Indian manufacturers by Honorable Minister on our Foundation Day in January. And other gas metrology facilities which have been set up at NPL in the recent past include the ones mentioned here. So basically, facilities to evacuate and filling the system, the cylinders. So there is an equal arm balance, right? And also new gas standards, which I'll show a little later in the Bharatiya Nirdeshak Dravya category, right? So we also successfully participated in intercomparisons. With pretty acceptable values in these cases. So it's an indigenously developed PM 2.5 samplers. This also got inaugurated or launched by Honorable Minister in January. So this is a technology which is transferred to the industry. So this is a PM 2.5 and PM 10 sampler. So this is one of the units is on display in the exhibition. Right. So the other major activity is in terms of the biomedical device standards. So for the first time, we have launched the calibration and testing facilities for defibrillator as well as infusion pump. And also working towards other parameters like the electrical safety currently. Right. So there is also a lot of work, COVID-related work, which has come out. So related to the PPE gown testing and calibration services. Right. So there is activity related to the development of sensors. These are not commercial devices yet, but then the prototypes have been demonstrated combining both 2D and 3D materials. So for example, MOS2 and gallium nitride based broadband photodetector. Then you have this self-powered UV photodetector based on gallium nitride nanotowers. This palladium tin oxide based carbon monoxide gas sensor has also been demonstrated. Right. So in the carbon group, which is again very active, so we have this oriented CNT carbon nanotube sheet setup. So this is image of aligned carbon nanotube based sheets. The rolls have been prepared, and then using the belt spinning assembly, so long pitch-based carbon fiber has been pulled. So various applications and interaction with industry is being carried out currently to find the applications of these. Right. Again, for the PPE and the COVID-related things, so the water vapor transmission rate through non-woven and plastic barriers is studied. There is one in-house development of computer-controlled printer. So basically, the printer is in-house developed for A4 size printing of photovoltaic, basically the perovskite solar cells. So we need, as Dr. Takate mentioned in his presentation on the first day, so we need a thermal evaporator for large area deposition, metallization. So then we can actually make go towards this large area device fabrication. So in the BNTs, the certified reference materials which have been released from 2021 till date. So with RMP partners and in-house, so we have released about 4 chemical BNTs. These cover mostly water with metals and non-metals, as well as the conductivity references. So high purity gold and silver have been released with Jalan. So the chemical BNTs are with Ashwi Technologies. And the cement BNDs have been released, 2 of them with NCCBM, the cement board. And in-house, like some chemical BNDs, these are mostly like 5 of them, including gases, which I mentioned a little earlier, as well as UV visible standards for spectrometers. Okay. So other very vibrant activity which NPLI is known for is the time and time dissemination. So the performance of UTC NPLI is shown from say 2020 to 2022 2-year data shows that like so we have pretty good stability, and we have a large number of both strategic as well as industry customers. Our NTP service is accessed by about 200,000 internet users. Okay. So this is another important development where the LF voltage team, so it's working on this phasor measurement unit as a meteorological tool for real-time monitoring of Indian smart grid. So this is something which we are working with the Power Ministry as well as trying to see like if we can introduce this as a standard facility for where the smart grids across the country, the power utility as well as power generation companies can make use of this towards next generation calibration and power sector. Right. So these are luminescent and bioluminescent pigments which are developed in-house. So these have been qualified by both the government meet as well as the private industry that these are as good as any commercial pigments which are available. These are mostly for, again, security applications, whether it's in currency notes or in passports and other applications. So a furnace has been installed with up to 1 kg synthesis of pigments in these furnace. So we're looking at technology transfer in the near future to a private partner. So we also revived the single photon metrology activity. So mostly on this superconducting nanowire-based single photon detector and silicon photomultiplier, which is a large area silicon APD detector. So this is for single photon detection, and the lab is being set up for the metrology activities. The cesium fountain and ytterbium ion trap for time standards. So these are we restarted. Hopefully, we'll see at least a fountain working in the very near future, and ytterbium ion trap in the coming future. Right, the sound primary standard as well as electrical standards are being revived, and upgraded currently. So we have developed quite a few technologies during the last 1 year. These include the development of polystyrene films. So these are highly transparent polystyrene films, which has been transferred to a industry partner. And for the solar cell industry, the process for synthesis of fullerenes accepted for organic solar cells. So this has been transferred, and also they have started supplying this to the customers during the last 1 year. So this is a UVC disinfectant. So there are 2 aluminum tubes through which the air is circulated before vented out. So these are good for small offices, homes, and even hospitals. So the technology has been transferred, and we're looking at commercialization of this. So the other technologies which were developed include the ultrasonic pulse velocity tester device. So then there is a device to use conventional ultrasonic flaw detector and the facility creation and installation for the design, development, fabrication, and testing and calibration for clinical thermometers. Right. So we also have filed a few patents, and then these are the copyrights which have been filed. And in the future, like, so we are looking at these two developments. Right. So we have signed about 7 memorandum of understandings or agreements with industry, universities, institutes for development of various meteorological facilities, as well as transferring the technology which is developed at NPL. Right. So we could successfully reach the pre-pandemic levels in terms of the total earnings last year. So there was a dip due to COVID in the previous year, but then we could regain our ECF. Right. Just to summarize, strengthening of existing meteorological services and expanding them to cover future needs of the nation. So this is the target which we are looking at. Towards this, we are looking for this PMU calibration to quantum metrology standard, setting up these facilities. We're working on biomedical devices to photovoltaic primary standard, which may come up in the next 1 year with the help of PTB Germany. So we are also recognized for air and noise pollution activities. So the air monitoring, both emission and it's like, so we got the gadget notification identifying NPL as an authorized calibration and certifications. I mean, for the indigenously made devices. So we are also looking at recycling solar cells. So one aspect is about recycling the precious metals, but recently we also succeeded in purifying and getting silicon itself. So this will be another important activity for us. So the BND is the certified reference materials covering a broad range of materials have been released, and we are working on many more. And we're also looking at the possibility of having our own indigenous reference solar cells, which we can supply to the local industry as well as institutes. Right. So the materials for metrology to sensors and their certification is the other area. So the materials is a very strong group in NPL, so we need to leverage. So we're working on integrating materials with the metrology activities so that we can do much more than what we are doing currently. To contribute as NMI to the quality infrastructure in India as well as in the APMP region, especially through the PTB SARC. So we are engaging ourselves with the policymakers and Bureau of Indian Standards, Quality Control of India, and Legal Metrology. So we striving to be an active participant in APMP and BIPM activities. So we hope we'll continue our journey forward. Thank you.
Thank you for this overview of, and good to see so much going on at NPL, and also revival after the pandemic. So any comments or questions from the audience? So if not, I think it was online chat. No. Okay, so thank you for a nice overview, and very good to see so much work going on in spite of all the problems of the pandemic. Do we have the so अच्छा है तो फिर चलो तो है नहीं ठीक है. So our next speaker is Professor Chunhui Li from NMI China, NIM China. He's the chair for TCFF for APMP. Oh, sorry. She's the chair for TCFF APMP. So I welcome Dr. Li.
Hello, can you hear me? Okay, thank you. Hello, everyone. I'm Chunhui Li, come from the National Institute of Metrology, China. I'm very happy and feel very pleasure to here to show our recent works on high pressure gas flow facilities in China. There's three parts in my presentation. First, I will introduce the background of our research. Second, I will introduce the available achievement in this field in our lab. Finally, I will make a short summary and the outlook. Firstly, on the background of this research, as we know, with the industry developing, the severe environmental problem occurred. So in order to protect the environment and protect the earth, in 1988, the IPCC was created by the UN Environment and the WMO. For the IPCC, the important output is assessment reports. The reports are a key input into the international negotiations to tackle climate change. In 2014, the number 5 report was released. The report provided the scientific input into the Paris Agreement, which aims to stress the global response to the stress of climate change by holding the increase in the global average temperature to well below 2 degrees C above pre-industry levels and to pursue efforts to limit the temperature increase to 1.5 degrees C above pre-industry levels. At the beginning of this year, the newest version AR6 was released. As you know, China is the biggest developing countries. We have the responsible to work with other economics to protect our Earth. So on 22nd September 2020, our government announced that our carbon aim. It would peak carbon dioxide emissions before 2030 and achieve carbon neutrality before 2060. In order to achieve the object, our carbon object, in fact, there's many research and investigations in China already. According to the available investigation in China, currently in China, there are about 3/4 carbon emission coming from energy-related area. You can see from this picture, in 2020, you can see the main energy source is coming from the fossil type energy. It dominates the energy consumptions in China. It takes about 85%. In order to achieve the carbon peak object, there's many research. We hope in 2030, the fossil type energy, the total consumption will decrease to 10%. It will decrease to 75% for the total energy consumption. And when our carbon neutrality achieved in 2060, at that the renewable type energy will dominate the energy consumption. It will take about 75% energy total consumption. But as we know, this object cannot be achieved one step. To guarantee the economical growth and keep the safety of the energy. For the fossil type energy, for the same energy output, in fact, the carbon emission from natural gas is about 50% relative to it from coal. So natural gas industry continuously to develop during the energy transition as the low carbon fossil type primary energies. You can see from this picture, you can see the total consumptions of natural gas dramatically increased recent years. In 2010, the total consumption is over 100 billion cubic meter in China. In this year, although there are some pandemic effect, the total consumption of natural gas will be expected over 400 billion cubic meter. And with the natural gas industry developed, currently there are about 1/3 natural gas imported from other economies. And since 2022, China already become the biggest LNG imported countries. You can see our LNG imported increased dramatically recent years. As we know, the flow is it is the key component, key parameters for the natural gas trade. So in order to guarantee the trade fairness of the natural gas, the first natural gas station was built in China last end of the century in Chengdu, Sichuan province. In this, for the first natural gas stations, we built the empty facilities as the primary standard. We use the sonic nozzle as the master meter for the secondary standard, and use the turbometer as the master meter for the working standard. After that, we also build the stations in Nanjing and Wuhan. For the 3 natural gas stations, they all have the primary, secondary, and working standard facilities. But in order to satisfy the requirement for the flow meter calibration, currently, besides about 3 natural gas stations, we already build other 6 natural gas stations in other provinces. They don't have the primary standard, they only have the working secondary standard and working standard. And in recent years, we also build 2 additional natural gas stations in Shanxi and Beijing. They don't have the primary and secondary standard. They only have the working standard to achieve the calibration of the flow meters. Although we already have over 10 natural gas stations, but unfortunately, before we don't have the chance to make any formal comparisons inside of China. So as the National Metrology Institute, we started the work to build our own high pressure gas facilities to achieve the comparisons, to pilot the comparisons in China since 2010. Our high pressure gas facilities consist of 3 facilities, including the Pvtt primary standard and a sonic nozzle secondary standard and closed loop working standard. The turbometer as the mass meter in the closed loop facilities. This is the layout of our facilities. The high pressure facilities use the same compressed air as the supply, as the source of the system. The Pvtt facilities was located in the single room. the sonic nozzle and closed loop facilities were located in the same room. The Pvtt facilities is the primary standard in our institute, so the accuracy is important to for us. The principle for Pvtt facility is very simple. The volume for the PV for the collection tank is can calibrate very well, so we can we can measure the pressure and the temperature very accurately for the collection tank. But to guarantee the best uncertainty, there are additional uncertainty components. We call the inventory, the mass change in the inventory volume, and the additional time corrections for the filling time. So finally, the uncertainty of the for the Pvtt facility can be expressed like this. To achieve the best uncertainty for the Pvtt facilities, we make a lot of work. Finally, with the special designing of the three-way valve, we achieved the mass cancellation in the inventory and the minimize the time corrections. This is the structure for the three-way valve. When at the beginning, the flow through this way, three flow outside in the bypass directions. During the filling process, the bypass valve closed firstly. So in principle, if this these two valves was closed, the pressure in the inventory volume will be dramatically increased. Finally, the valve connected to the collection tank opened. With the idea, we make the measurement for the opening and the closing process. The high-speed pressure transducers was mounted in the inventory volume. So you can see here, when the timer is triggered, the pressure in the inventory volume was increased. So the result supports the designing the idea. Finally, the mass cancellation was achieved in the inventory volume, and due to the good symmetry of the closing and the opening process, the time correction is smaller than 10 milliseconds. Finally, the uncertainty for the discharge coefficient of the sonic nozzle will achieve 0.08%, and the capability was verified with the comparison in 2016 among PDB, NIST, LNE, and NEEM. This picture show our sonic nozzle facilities and closed loop facilities. For our sonic nozzle facilities, there are 16 sonic nozzle was used for the master meters. You can see from the left picture that there are the yellow turbine meters. There's 4 yellow turbine meters used as master meters in the working standards, the closed loop facilities, to guarantee the best uncertainty of the closed loop facilities. And there's additional pipelines for the customers, the customers flow meter. The principle for the sonic nozzle is like this. Finally, the uncertainty can be expressed like this. The biggest challenge for the sonic nozzle facility is, you can see here, the pressure range for our sonic nozzle facility is from 100 kPa to 2500 kPa. So the pressure range is relatively large. And so how to calibrate 16 sonic nozzles, how to achieve the best uncertainty for the nozzle is the biggest challenge for the sonic nozzle facility. Finally, for each nozzles, we calibrate at least 9 pressure points. And to achieve the best uncertainty for each nozzle, we make the curve fit on base of the calibration result. And the curve fit formula is chosen according to the principle of the sonic nozzle. Finally, you can see here the residue for the curve fit is relatively small. Finally, the uncertainty of the sonic nozzle will achieve the 0.15%. And the uncertainty was supported by the comparisons between PDB and NIM. Last, I will introduce our closed loop facilities. In fact, the closed loop facility and the sonic nozzle facility was located in the same room, and they shared the most pipelines. When the closed loop was used, you can see the flow, the gas will flow like this directions. The meter and test was mounted in the downstream of the master meter. The principle of the closed loop facilities is similar like the sonic nozzle facilities. So finally, the total uncertainty like this. The challenge for the closed loop facilities like the sonic nozzle facilities, how to achieve the best calibration result and make the curve fit. Finally, according to the principle of the turbine meters, we make the 5-point pressure calibrations for each turbine meter. For each pressure, we calibrate at least 8 flow rate. So finally, the uncertainty for the closed loop facility will achieve the 0.2%. The verification for the capability of closed loop facility was made by the comparison between the sonic nozzle facility and the closed loop facility at different pressures. You can see the result like the pictures. Besides the turbine meters calibration, there's another challenge for the closed loop facilities is the temperature control. You can see for this calibration, the results relatively scattered. The reason is the temperature control. After about 2 years operations for our closed loop facilities, currently the temperature change can be achieved with 0.3 degrees C in 1 hour. After our high pressure gas facility was built and verified with the comparisons with other economics, in fact, since 2016, we began to we started the domestic part comparisons. The comparison was consisted of 2 parts. The first part for the primary standard comparisons, we use 4 sonic nozzle as a transfer meter. The second part is the secondary standard comparisons. We use 3 turbine meter as a transfer meter. As we know, the PDB is a pilot for the high pressure comparisons in CCM fluid flow field. So in order to guarantee the result consistent with other economics, in the domestic comparisons, we also invite PDB participate to support our support our result linked to the key comparisons. With the 4 sonic nozzle as a transfer meter for the primary standard comparisons, finally we total got over 100 measurement result. To cover the Reynolds number, we developed the theoretical equations to analyze the result. For all the results, we can see the maximum difference was within 0.2% between the reference value and the measurement result. And after the primary standard comparison, we also organized the secondary standard comparisons. Here we use 3 turbine meters as the transfer meters. We got totally about 300 measurement result. There are over 97% result within the consistent rhythm. I think it is good enough already in this stage. Last, I will make a short summary. In fact, since 2016, after our high pressure gas facility was finished, we already organized and participate the international part comparisons to verify the capability of the facilities. After that, we organized the domestic part comparisons for the primary standard and secondary standard. And in this year, in fact, we will participate in the key comparisons. And for the domestic part, we will organize all the natural gas stations comparisons in the near future, especially for the working standard facilities. Besides the natural gas field research, in fact, you know, for the natural gas, it is the low carbon fossil type energy. For the hydrogen, it's zero carbon emission. So currently, there's a lot of research in China for the hydrogen. In fact, in China, at the beginning of this year, as you know, the Beijing Winter Olympic Game was held in China. In these Olympic Games, the hydrogen was used to light the Olympic torch already, and there were more than 1,000 hydrogen fuel cell vehicles and over 30 hydrogen refilling stations were used. So the requirement for the high accuracy measurement for the hydrogen is strong. So as the National Metrology Institute, we already cooperate with other institutes and companies to start the work in the hydrogen field. First, for us, we plan to build the sonic nozzle facilities, which make the traceability to the Pvtt with air, from hydrogen to air. And then in the near future, we also plan to build the MT primary standard in the field of the natural hydrogen. That's all. Thank you for your attention. Thanks a lot.
Very thorough presentation, detailed presentation on fluid flow measurements. Any questions, Dr. Jaiswal?
Dr. Lee, good morning.
Good morning.
One question, what you told about your high flow facility. So what are the primary standards using for the low flow? What are the primary standards you are using for low flow? All these are
for low,
yeah, low flow.
Low flow, yes, for the Pvtt facilities, the flow range from 0.019 kilogram per hour to 1,000 kilogram per 100. Because for our Pvtt facilities, we have 2 collection tanks. For the small flow range, we use the smaller collection tank. For the higher flow range, we use the bigger collection tank. So for us, the primary standard is the Pvtt facility.
That's good, because I was just thinking about your 2,000 liter Pvtt. I was not aware. Yeah, 0.1 liter.
Yeah, we have 2 Pvtt. One is 2 cubic meter. Another is 0.1 cubic meter.
Thank you. Thank you very much.
Thank you.
Thank you. Any other question?
I have a question. how do you determine the volume of 2 meter cube vessel PVTT?
Yes. In fact, before we use the PVTT facilities, we use the pure nitrogen to calibrate the volume of the PVT, the collection tank. We use the balance to weight the initial and the final mass for the pure nitrogen. So finally, according to the mass change and the density change in the collection tank to calculate the volume of the collection tank.
So what will be the absolute vacuum you are generating?
You mean the volume?
Vacuum. PVTT. Initially.
The PVTT. You mean the PVTT uncertainty? Yes.
From atmospheric pressure, you will go to vacuum or always use at a elevated pressure.
You mean the vacuum pressure? Yes.
Yes. If you are using PVTT for atmospheric pressure intake, then you have to go for negative pressure in the vessel, or you always use at a higher pressure in the upstream.
Yeah. For our PVTT facilities, first we evacuate to about 100 Pascal. Then we fill into it to 100 kPa, and the pressure range for the stagnation pressure for the PVTT from 100 kPa to 2500 kPa.
Okay, thank you.
Thank you.
So once again, we should thank Dr. Lee for an excellent presentation.
Thank you.
Thank you, Dr. Lee. Now time to move on to the next talk. So the speaker, yeah.
Then his slide.
So. Okay. So anyway, the speaker's introduction, I'll give Dr. Jeff Gust, who is the Chief Corporate Metrologist for Fluke Corporation. He started his career in metrology from 1985, and he's been serving on the board of NCSLI, Board of Directors, in various roles, and currently he is served also on ILAC Proficiency Testing Working Group and was a writing committee member for the development of ISO 17043, etc. So very important hardcore metrologist. So what are we doing? Just listen to the slides, look at the slides.
Good morning, all. I'll be presenting on his behalf. Good morning. So I'll be presenting on his behalf. So just now I have been given this responsibility. So I try to do my best to present his PPT. So it's on the importance of understanding customers' tolerance for risk regarding calibration services. So risk is very important, and it has been included in the 2017 version or the revised version of ISO 17025. So it is one of the notable changes in ISO 17025 2017, And in clauses 713, so this clause 713, so it says that when the customer requests a statement of conformity to a specification or standard for the test or calibration, so like for it's a pass, fail, intolerance or out of tolerance, the specification or standard and the decision rule shall be clearly defined. Okay. And unless inherent in the requested specification or standard, the decision rule selected shall be communicated and agreed with the customer. And 786 is about statement of conformity or the decision rule. So decision rule, so it is the rule that describes how measurement uncertainty will be accounted for when stating conformity with a specified requirement. So these things, and why were these changes to ISO IC 17025 made from the previous version, which were in 1999 or 2005, and how does it affect the calibration laboratory and the customer interactions? And why do we have statement of conformity? So it is going to be answered in subsequent slides. So as a background, so our customer or manufacturers, they build and make many things. Sometimes they are simple, other times they are very sophisticated. Our customers can't sell these products if they don't meet their published requirement specifications. So the decision to ship or reject a product is based on measurements. Measurements from measuring and test equipment, or in short, M&T. So how does manufacturer know that their measurement and test equipment is correct? So they need to get it calibrated and tested from the NMIs or accredited labs for 17025. As mentioned, as per ISO 9001:2015, which is management system requirements, and in one of the clauses, 715, it mentions the organization shall determine and provide the resources needed to ensure valid and reliable results. When monitoring or measuring is used to verify the conformity of products and service to requirements. So conformity is basically fulfillment of a requirement of the standard or the specification which the manufacturer is mentioning. The organization shall ensure that the resources are provided and those resources are suitable for the specific type of monitoring and measurement activities being undertaken and are maintained to ensure their continuing fitness for their purpose. And the organization shall retain appropriate documented information. So it's very important that the organization need to retain the documented information as evidence of fitness for purpose of the monitoring and the measurement resources. So if a company wants to make good decisions, they base them on measurements, which requires calibrated measuring equipment to have confidence in such measurements. So they need to get it calibrated. And from customers review, customers, they do review the calibration certificate that is provided to them to understand that their measurement and test equipment is in fact correct, which means whether they are pass or in tolerance or not, that is, out of tolerance or failed. So the results of a calibration can be presented in many ways. Customer wants that the information to be presented in the most simple and unambiguous way should be very clear. I mean, the simplest form could be either pass or fail. So for decision rules, the most important question of this presentation. So what is the rule or method that the calibration lab uses to make a determination of pass or fail? And what should be the basis of this decision rule? The end result of a calibration and verification is generally a decision. So to accept good units or to reject bad units. Now, when performing a measurement and subsequently making a decision regarding the statement of conformance with an identified specification, such as in or out of tolerance to a manufacturer's specification, so there are two possible outcomes, that you are right or you are wrong. So, this is the specification limit. So at the center, the nominal value and the lower and upper limit. So if the assigned value and the measurement uncertainty, so if it is within the limits, lower and upper limit, so this is the case of clear pass. It is within the limits. But if your measurement capability or the uncertainty is higher than the tolerance, that is the lower and upper limit of this manufacturer's specification. And if you are giving the decision on this basis, so there is a risk that it is a false accept. If you are accepting, it's a false accept. So if your uncertainty is large compared to the specified requirement, how confident are you in your declaration of intolerance or out of tolerance? So when an instrument is declared intolerance, but the instrument is actually out of tolerance, so it is referred to as a false accept. And when an instrument is declared out of tolerance, but the instrument is actually intolerance, it is referred to as false reject. And this false accept is consumer's risk, and false reject is manufacturer's risk. Okay. So false reject produces risk, and then it involves the cost money by requiring unnecessary adjustment, repair, or replacement. Whereas, as I mentioned, that false accept is the consumer's risk, because there is a probability that it is outside the limit. It could be outside the limit. So it costs everybody money by putting out of tolerance test equipment in the field or in the market. So the chance of making a false accept or false reject can be understood as a probability, which is usually expressed as a percentage. So when a customer requests a calibration, they usually don't worry about false reject risk. May specify a maximum acceptable false accept risk. So each decision rule has a different level of false accept and false reject risk. So it is important that the calibration laboratory and the customer, they should agree to use a decision rule based on the amount of false accept or false reject that the rule may contain. So a decision rule should be used that has a level of risk that is appropriate for the customer. So does your customer know the level of false accept or the false reject risk they are willing to accept for the calibration of their products? The answer is most customer don't know this. So this US Navy, for the nuclear weapons program, they choose 1% as for tolerance, whereas ANSI or NCSLI specify 2% probability of false accept or PFA for this. So it is good to understand what your customer does to understand what level of risk they can tolerate. So it depends on the type of the product So are they building a DVD cases or airplanes? Because then the tolerance limit depend on the products. In this case, of course, when one goes for airplanes, it has to be the best possible tolerance. Some customers will specify their probability for false accept. So if this is the case, then you need to select a decision rule that meets customers' specification during contract review. Because in 713, what we have, then while reviewing the customer's query, so, and if the customer asks for the statement of conformity, so it need to be finalized during that contract review and it has to be agreed with the customer. And if it is inherent in the standard, that the risk is covered in that standard. But if it is according to the specification, and if this customer specifies the specification limit, but for the cases of false accept and false reject, so that need to be agreed during the contract review before the commencement of the calibration or testing. If they don't specify a PFL, you can take a low, medium or high risk approach for selecting a decision. So here, in such cases, the laboratory need to, carry out the risk analysis in very detail, in elaborate form. So measurement is decision risk requirements. So for low, 1% or less, whereas for medium, less than 2%. For high, it could be more than 2%. No such thing as zero risk. Risk is involved. The lower the risk, the more expensive the calibration cost. You may want to consider decision rules that will meet most customers' risk requirements. So Fluke has a 2% PFA requirement that is coming to medium, but more often select decisions that are less than 1%, which is under the low risk category. So in the revised version of ISO IC 17025, which is revised in 2017, now the calibration laboratories can understand that in 713, when the customer requests a statement of conformity, why the specification and decision rule needs to be defined and agreed with the customer before the commencement of the work. Also, why in 786 requires when a lab makes statement of conformity, they need to document the decision rule. So this document the decision rule as an evidence and take into account the level of the risk. So this implies that the lab knows the level of the risk for the decision rule. It empowers the customer by requiring both parties to talk during the contract review and agree to it. So it is a change from the previous version of 17025, which were in 1999 or later on in 2005. So the measurement decision risk was not taken into account at all regarding statement of conformance in previous versions. So it was in the hands of laboratory to do what they wanted. Now to conclude, the best calibration services are performed by organizations that are committed to technical competencies provided as per ISO IC 17025, that is for calibration and testing services. And these services are focused on meeting the needs of their customers by providing calibration decisions that are easy to understand and with an appropriate level of risk. Calibration laboratories must understand the risk associated with their decision rules, and they need to talk with their customers about risk, educate them, and understand the appropriate level of risk that they can tolerate. Thank you. Thank you.
Excellent.
Thanks.
Without any preparation. For Dr. That's very happy. So we don't take any questions on this. Any comment if there's something we can do? Somebody had something to add? Anyway, so now we hand over to the organizers.
I thank to all speakers for sharing their expertise and knowledge with us. Now I request Chairperson of the session to felicitate Dr. M.A. Ansari with conference memento. Thank you so much, sir. Now I request Dr. Sanjay Yadav to felicitate Chairperson and Co-Chair of the session with token of remembrance. Thank you, sir. Now you all are invited for having tea in front of auditorium. We will gather back for upcoming events after 15 minutes at 11:30 a.m.